Did that happen? Yeah, it's happening. All right, so here, this is just saying the idea of a set of languages being closed under an operation. So this is the set of all DFAs, all languages that can be solved by, say, a DFA. And what does it mean to be closed under some operation like union? And this just says if a language can be solved, I guess this circle got smaller too. This circle used to be bigger. When a circle that surrounds all of these is that circle supposed to be. Right, so if this language can be solved by a DFA, then it has a machine, and if this can be solved by a DFA, then it has a machine, and you can take those machines and build another machine that can do the union. Everybody follow that part? And so that's, And here we talked about this. We did this method on the test. So that's, everybody know how to do that part? This is how to do two machines at the same time. Any questions about it? And so here are the two machines running, right? This gnome knows where both of those machines are. Right, we just took that up on the test. And here's how to do concatenation. So for a DFA, the concatenation doesn't work, right? Because here this state, what you like to think is, we just put an edge, to connect the end of one and the start of the other, but then this node might have more than one A leaving it. And you haven't committed, right? You can do something here, you can go over there, and you can come back, right? So in contrast, this does work for an NFA, right? We put in these epsilon transitions from the final to the next, and remember with the epsilon, I've joked about it being like a marriage, right? You have to commit that I'm moving along, right? Everybody buy that? So if it's in both, then it's in the combination. So this was how we did this on the test, right? Everybody remember that? That's for doing stars. People getting this? Or I just stuck them up because this was a review of the whole. All right, this one we hadn't done before the test. And so this is, if you're doing NFAs and you're doing union, then you don't have to do a cross product. You can say, well, you can bring an epsilon to either one. And again, the epsilon is doing a commit. I commit to it being this language, or I commit to being that language. Right, and for intersection, it doesn't work. So you have to go back to that. Complement, we've talked about how complement doesn't work for an NFA. All right, so this is where I really wanted to be getting to, just a review of what was going on here. So I think this is worth having just the high-level understanding of what's going on, right? So you have a DFA that, this is an NFA, right, non-deterministic. So what you should know how to do is there, a gnome will be on a state if there exists a path that would get you there, right? It's all back to the alpha state, right? Or the M, remember the M of a state is the set of strings that have a path to that state. And so given a string, we can have a gnome on all the states that there's a path to for that string, right? I mean, it's in some ways what we're doing is here's all possible strings, and here the various states. So when we talk about L of or the M of a state, we're talking about which strings will end up in this state, right? And conversely, if we're talking about a string, we can say which state should have gnomes on them, right? Does that make sense? And so here these, right? And then how do we build the DFA is, remember we just did that example in the test with you read the A and then this path, and the number of states blew up exponentially. And so in general, and so they can blow up exponentially, and how we build the DFA is for every subset of the states, we have a state here. And what is this gnome remember? This gnome knows that given the string so far, there's a gnome here, here, and here in the NFA. People get that? Yeah? Uh-huh. Mm-hmm. So what you do is if you have an NFA and you want to convert it into a DFA, what you do is for every subset of the states, you're going to have a state down here. All right. So here, 1, 2, 3 is saying there is a gnome on 1, 2, and on 1, 2, 4. Good thing I can read 1, 2, and 4. Right. And so now, suppose I'm in this state here, right? Then you can say, what happens, right? If I'm in this state here and I get a B, well, what does this gnome do? If it gets a B, it can, it could zip over here and read that B, and this gnome could read that B, and this gnome, well, actually, it could follow these epsilons and read that B. But really, they're all going to end up here, right? Depending on quite how you define gnome transportation, epsilons, they're all going to end up here. So if I'm in this state and I get a B, then what happens is we move over to this guy's, and I don't know why he's so far over. Things kind of moved when I copied them, right? And so now I'm in a state where there's only a gnome in B. Does that make sense? So those are the ideas that I think it's good to know, right? All right. So and then how to build this is building given an extended regular expression, how do you build the DFA? And this is, I think, just good to know how to do recursion in general, right? So in recursion, I'm given an input, and I can give anything to my friends as long as I can give them something that meets the precondition and is smaller. Right? So if I'm given, my goal is I'm given a regular expression and I want to build the DFA. So this is only one page of it, so it's only one example. But suppose my example is I'm given this string here, then what really is it? It's, if you parse it, this is one regular expression, and this is another regular expression, and we take the intersection of the two, right? So I take this big first piece, and I call this first piece R1, and I give it, and I recurse on it. And what does it do is, extended. I was like, I don't remember what the E was. But it takes an extended regular expression. Here's an extended regular expression, and it turns into a DFA. Right? So now I have a DFA my friend gave me, that I didn't micromanage him. My friend gave me this machine and that does this language. And then my other friend, I give him this, and that friend gives me another machine for the second piece. Right? And then I say, oh, look at DFAs. I know how to take the intersection. Oh, that's an intersection, not a union, right? How do I do the intersection, right? I build a machine that way. Everybody kind of follow that? Yeah? Well, maybe I didn't spend enough time with you guys on this. I'm not sure I even ever said it. Where brackets go, right? If you say 3 plus 4 times 7, and you say 3 union 4 concatenate 7, then you have to know which have higher precedence, right? And here the implication is you're doing that, and here the implication is you're doing that. Did that answer your, right? So the kind of the last thing that happens, if you were to do this in order, the last thing that happens is that, right? As opposed to, right, I take the intersection of A star and B star and concatenate it to that. And all right, and so, here's just running through an example, right? So we had this and this, and so if I have this, and I give this to my friend, and what does my friend do? My friend gives this to his friend, and what does this friend do? This friend sees it's a concatenation of 4 things, and the friend builds each of these, right? This one here accepts just 1, and this thing here accepts 0 star, right? And then we concatenate them together, and we build up. Does that make sense? And this is a one slide on how to convert NFAs to regular expressions, right? So you have some crazy NFA like, you have some crazy NFA, and you want to build a regular expression for it. And how do you do it? Is you don't do it on all one step. You're going to a loop invariant, an intermediate thing, is that we're going to have this new weird machine. I guess we're calling it GFA, generalized. I don't know what the GFA stands for. Anyway, what it has is it looks like an NFA, right? Except the edges aren't necessarily single letters. They can be whole regular expressions, right? And so this is, and what are these little letters down here? Here I gave various names to it. I call this state QI, QJ, and QRIP. Why? Because that's the one I'm going to rip out. And then I'm given these regular expressions names. And what is it? This is some regular expression like this. And what it says is, if the gnome travels from here to here, then what it's kind of reading from the input is any string expressed by that regular expression. Right? Does that make sense? And so then, how do we say, what is this equivalent to? Well, this is equivalent to, well, I could go from here, how do I get to there? Well, I could go directly, so I get the regular expression that goes from I to j, and so that's bit. Or, and here's the union is an or, right? Or I do this regular expression, and then we do this regular expression from here to here is as many times as I want, right? That's the star here, and then I come back down. Does everybody see how these two are kind of related? And you certainly can imagine you don't want to do this, but you have some big NFA, you choose some state, and you rip that state out. And as you rip that state out, every other edge in the machine is going to, as we rip it out, we look at the triangle for that other edge and how it gets updated, right? Yeah? Oh, where do we start? The two states? No, I would say this is just one little, there's a big, big one of these things. Lots of states, and between each state, when we first start, is you have a big NFA, and between every pair of states, there might be an edge with a character. And what have we done? We've moved along, and now we have fewer states, and between every pair of edges, there might be an edge. For every pair of states, there might be an edge with some regular expression. And now we're zooming in just to, we're choosing one state that we're going to rip out, and we're choosing one edge that we're going to update. And so we're going to, when we rip out this one state, we're going to have to update every edge. And how do you update that edge? Is when this state goes, you replace the label of this edge with the label of this. And so when you say start, I'm not sure what you mean. Yeah? Everybody kind of follow that? And, all right. So here's another concept. And so each of these, right, we're giving a page of understanding, and there's going to be a little question where you have to answer various things about it in the next test, right? So here, we want to understand why this is all, the goal is to prove that 0 to the n, 1 to the n isn't computable by a DFA, right? And everybody should know what this represents. It represents, you can have as many zeros as you want, any number of zeros, and then the number of ones has to be the same, where n is greater or equal to 0. Right? Everybody understand this language? And then we could say, we could have two, and so why is this uncomputable? Right? In my own words, I would say, well, it's uncomputable because the DFA, or even if it was an NFA, I don't care which, it has to read the zeros. At some point, it's read the zeros, right? And what does it need to remember? I say it needs to remember exactly how many zeros there are, because later it's going to read the ones, and it has to be the same number, right? So it has to remember, and if it's going to remember the number of zeros, then how many different things might it need to remember? Well, n could be 0 or 1 or 2 or 3 or 4. There are an infinite number of things that it could be, right? Here's a funny thing is each integer, 1, 2, 3, 4, is finite, but the number of them is infinite, right? So the number of things it needs to remember is infinite, and so how does it remember different things? Is by being in different states. It needs an infinite number of states, right? Does that make sense? Another way of looking at it is saying, let's say we remember the picture, maybe it is even coming up. Two boys communicating, right? The first boy Their communication line is sitting right here. Let the first boy see this. Let the second boy see this. And the first one gets to send one message across. What's the message? It needs to give enough information so that the second boy knows whether the answer is yes or no. Right? And what needs to be communicated, you can sort of argue, well, this guy has to learn how many zeros there are. Right? So again, how many different messages could be communicated? Well, it's an infinite. N equals 0, 1, or 2, or 3. And again, how do we communicate that? By what state are we in at this point? Right? Does that make sense? And another way of looking at it is by this alpha beta thing. Right? So I'm going to say two first names, right? This is kind of our first name and our second name. Our first names need to be distinguished, right? Can you tell me two first names that need to be distinguished? Zero, zero, and 0, 0, 0, right? More generally, 0 to the I versus 0 to the j, where I doesn't equal j. Right? Here's our two different things that the first boy might have gotten. And we have to prove that he has to be in different states for them. He has to send different messages. Different things needed to be remembered. Why? Because the future, what is our zeta slash gamma slash sigma that proves that we need to distinguish between these? Yeah? 1, 1, right? Or more generally, 1 to the I, right? Because alpha zeta is a yes, right? And beta zeta is a no, right? So these need to be distinguished, right? Does that make sense? And hence, these need to go into different states. Well, we can design a set S, which equals 0 to the I for I greater or equal to 0. This is a set of these sets' first names. And I claim any two strings in here need to be distinguished, need to be in different states. And I have an infinite number of things in here, right? And hence I need an infinite number of states, right? And that's what that all says, right? Does that make sense? And this is just all more here, all what I just said, more of what I just said. Any questions about it? So I can more or less tell you, there's going to be a test on the next question, which is going to give me a good argument why something like that is not computed by a DFA, right? And you can say you can say these various things, right? Any other questions? And I think that does this whole set of slides, right? So in each of these, I can test you a little bit about, right, these transitions or, closure. This one up here, what does it mean for a set of languages to be closed? We can think about this, these various ways of closing. We can think about how this is a couple of sentences about going from a DFA to an NFA, right? And some understanding that the number of states is going up by an exponential, right? In fact, we're going to later be talking about non-deterministic polynomial time, where instead of a non-deterministic Turing machine or a non-deterministic DFA, we're going to, you let fairy godmothers help you. And what's computable there goes up by if it takes t time with the non-determinism, then it takes 2 to the t time with the deterministic algorithm. So it's the same sort of blow up in time. All right, that's it for NFAs and DFAs. I think if you followed all that, you'll be great for the test. Yeah?
That cannot be solved by an NFA as well, right?
Which?
The O to the N and 1 to the N.
Cannot, oh, an NFA as well. Yeah. Well, one, everything I said here was all about counting. It was information, and so it had nothing to do with NFAs versus DFAs. Everything I said would equally apply whether it was an NFA or DFA. Right? So that's one argument. The other argument I would say is, what did we prove? Sometimes it's good to be able to take various, sometimes I ask on a test something that you don't know, but you put together various theorems and you do know it, right? So what do we know here? We know for every NFA, there exists a DFA that does the same thing, right? And we know that there doesn't exist a DFA that solves 0 to the n, 1 to the n, right? And now, if you're all experts at 1090, which I think is probably stretching the truth, right? Then you should be able to put these things together. Some sort of nice 1090 proof would then prove that there doesn't exist an NFA to solve, right? Because if there did exist an NFA, then there would exist the DFA, right? But there doesn't exist the DFA, hence there doesn't exist an NFA. And I know the proofs that I saw in 1090 were crazy, but surely you could formalize what I just said in such a proof. Right? Everybody buy that? Yes? You got a bunch of zeros followed by a bunch of ones. Could you solve it personally? And they're finite, right? So this is all finite in, right? How would you do it? You would count the number of zeros, count the number of ones, see if they're the same. In fact, you could do a little better. You could count the number, count up while you do the zeros, count down while you do the ones, right? So a Turing machine could do that you could count in binary. Turing machine with one tape could also have an n-squared algorithm. It would cross off a 0, come over, cross off a 1. Come over, cross off a 0, come over, cross off a 1. Right? All Turing equivalent models of computation are equivalent to a Turing machine, not a finite state automata. Good question, right? Right, and so that's kind of why we're doing this. Is we talk about models that are equivalent to Turing machines, and we talk about models that are clearly weaker, right? And this one doesn't have enough memory to count, right? And that's kind of why it's interesting. That here's a problem. Here's a machine that can do all of these cool things, but it can't do this. Right? And, yeah. And in some ways, your laptop is a finite state automata, right? Because It only has a finite amount of memory. And could it, if you kept giving it zeros, eventually it would lose count. Right? So in some ways, your Turing machine, your laptop, is not a general purpose machine. Right? It's actually a finite automata. Right? The only reason we call it a general machine is, well, we're just sort of pretending that we won't run out of memory. Right? As long as you don't run out of memory, it can do anything a Turing machine can do. Yeah?
How would the Turing machine do it? Because the sum could be arbitrarily large, the number, the n.
Yeah. Yeah, so I kind of gave two methods. The one method, if there's just the tape where all you're allowed to do is write one tape, you're allowed to write blanks, right? You just blank out a 0, you blank out a 1, you blank out a 0, you blank out a 1. That would do it, right? Or if you had an extra tape, you could move the one head forward as you count in binary on the other tape, right? I mean, we kind of told how to compile from a Java program into a Turing machine. So I would say, using Church's thesis, if you personally, I would always call you a Turing equivalent, right? If you can do it, a Turing machine can do it, right? And so we're good. Any other questions about anything? Should we do more content? How much are we doing for time? Should we do 20 minutes? Should we do some grammars? All right. I haven't thought about grammar questions at all. I can tell you some of the grammar questions that I've had on tests in the past off the top of my head. I don't remember what's on the practice test either. We could go to the practice test. But let's do an example that's really quite practical. All right, what was the example? Oh, there was a tuple one. So, right, that's a tuple, right? And what's that? That's a tuple of tuples, right? So suppose we want to think about all of these various things, tuples of tuples. And so you can start by giving things various names, right? Let's say this is a tuple of tuples. Then how are you going to do a rule here? A tuple of tuples is what? You know, you can say it starts with a bracket, and then what do we have? Well, right, so here we want to say, well, here we could say, well, what's in here, right? So it could be a number, or, you know, we have to say what's going to be in there, right? So we could have a different name for that. And then, well, whatever that was, we're going to separate them by brackets, and we have some number of those, followed by a bracket, right? So is that how does that look? Right? I mean, we're saying a tuple is square brackets with some sort of objects in between, with commas between them, and it has to be a finite list, right? Everybody kind of follow that? I mean, in English, that certainly is reasonable. Is it a grammar? Why isn't it a grammar? We haven't really narrowed this down. And what haven't we really narrowed down? How many things are going to be in here? Right? Everybody kind of see that? So what do we do with, how do we, let's do something easier first. Give me a grammar for A star, right? It's 0 A's or 1 A's or 2 A's. In fact, all right, let's start with that. What would the grammar for this be? Let's call it A. A goes to A star. That's not a grammar rule. This is the name of this non-terminal, right? What would our rule be? Yeah. And the empty string, right? People get this? What is an A? What a capital A is some string of A's, right? Oh, I produced another slide. Let's see if I can find my other slide.